Thank you very much for inviting me to talk. This has been a wonderful conference. So I'm talking about this project that I took on last year. The aim was to compute rate 1 modular forms. The LMFGB only had rate 1 modular forms up to maybe level 4,000. And the upshot of this work is we managed to come up with a much more efficient way of computing them and managed to compute them up to level 10,000. So that's the work that I'm going to be talking about, and I'd like to acknowledge my supervisor, Min Lee, and also Andy Booker and Jonathan Bober, who I have many fruitful conversations with about this work. So straight away, I'm going to talk about essentially the motivation. There's this fantastic result of modern number theory which associates new forms, weight 1, Hecke eigenforms, level n, character chi on one side, with Artin representations, certain Galois representations that I'm going to explain a bit more what they are in a bit. And this association is done via L functions. The L function on the left is the same as the L function on the right. And the right arrow there is Deligne and Serre, and the left arrow is Kerr and Wintenberger. How's this shake out in the real world? So here's an example. Field Q along with the roots of x cubed minus x minus 1. And here's how various primes split over that field. This field has discriminant 23, so the only ramified one is this 23. But there's some other split. And alongside this question of how primes split over this field, we only have one Hecke eigenform of weight 1 and level 23 with quadratic character, and it's this one here. And what at one time would have been quite surprising, but now is fully known, is that the Fourier coefficients sort of encode this information of this seemingly unrelated problem, where if you've got an inert prime, you've got -1, whenever you've got split as 2 factors, you've got 0, and so on. So I said at the start, computed up to level 10,000. One implication of that is any such number field up to discriminant 10,000, we have this sort of information for. So I've hopefully convinced you that doing this computation, an efficient way of doing this computation is useful. But what's the problem here? Why exactly, when you read texts on modular forms, they always kind of treat weight 1 as a bit of a side note. And as an example, of your laptops here, if you type out this in pre, if you bring up GP and type this in, it will probably tell you the answer before I can finish this sentence. This is level 9995, weight 99, and this is character, and I've given it here in terms of Conway label. Or I'm going to be mentioning a lot of characters, and it will probably just be the Conway label. And it tells you very quickly, if you do this, that the dimension of this is 98,002. Now, if you change one of those numbers to weight 1, do everything else the same, one or two things will happen. Either you've been sensible and limited the amount of memory the pre is allowed to take, in which case you'll get a Stack Overflow error, or you've not been sensible and you've just crashed your laptop. Or this will take forever until well after the end of this talk before it actually gives you an answer to this question. So it's somewhat peculiar is that it really struggles with this weight 1, not even finding the forms, just giving us the dimension. And there's 3 reasons why this is. Firstly, weight 1 is non-cohomological. So all of your favorite techniques that you may want to use from modular symbols aren't really going to help us here. I don't know if Sage actually has a weight 1 implementation at all. It might just tell you to go away and do a different computation. Secondly, the discrete spectrum of the Laplace operator, weight 1. We can't separate modular forms from Maass forms. Maass, of course, had these raising and lowering operators that can raise or lower the weight by 2. Whenever the weight's more than, or at least 2, we can use the lowering operator because it annihilates everything associated with a modular form. So if we want weight at least 2, we can use the Eichelor-Selberg trace formula and get everything we want. by comparing with this lowering operator. Similarly, the sort of the dimension formula from place, and we don't have it for weight 1 again for this reason. Finally, as a last refuge, you might want to try and start doing finite field computations because they're really nice and easy, and your laptop likes finite. But this projection isn't necessarily surjective. So we don't really have much scope there either. If we do everything over a finite field, we might end up with forms which aren't the projection of a classical weight 1 form, these so-called ethereal forms. And they're very interesting. I sort of seem to have gathered clues that there might have been a talk on something related to this before I got here. Yes, they're very interesting, also associated with Galois representations, but for our purposes, they kind of just present a problem. They mean that we can't just work over a finite field. We're going to have to get our hands dirty and work over Q-bar at some point. So now I'm actually going to cover this notation. So a quick run through, because this notation has been everywhere over the last few days, probably over the last few weeks. H is going to be my Poincare upper half plane. Congruent subgroup, gamma naught n. So even though I'm doing stuff with character, so you could also do with gamma 1 n, but I'm just doing the lower left congruent to 0 groups. So then we have weight k, level n, character chi, is going to be this m k n chi. They've got Fourier expansions. That's really, when I talk about computing, that's what I'm talking about computing. I want to compute the Fourier expansion. And a reminder of this Stern bound, which grows in weight and level. When I talk about computing a weight 1 modular form, or a number of other things, I'm really talking about computing all of these Fourier coefficients up to some limit, some arbitrary limit. And often we can just take that to be the Stern bound. Some operators and spaces. So firstly, just these operators. So I'm going to be using the Hecke operators. I'm going to be using lifting operators, and one maybe slightly less common, I'm going to be using this twisting operators. So Hecke operators you'll be familiar with, defined like this. This is full generality. This is like Ivaniet kind of notation. Lifting operators, yeah, it's just f of rz instead of f of z. And then twisting operators, we multiply all of the nth Fourier coefficient with psi n for some Dirichlet character psi. And this takes cusp forms to cusp forms, and we know Hecke operators will fix the character and level. Lifting operators fix the character, but level, I've put m multiple of Rn. Just takes us to any multiple level, really. And then twist, it changes the character to chi psi squared. And level, I've just put m. We know what level it is, but it changes. It could be greater, it could be less, depending on the situation we happen to be in. But there are fleshed out explanations of what level we end up at. So that's known, but I've just put m there. So then all of our spaces, well, S, K, and chi, that's the cusp space. I'm going to use this E to be the Artin space. Forms arising with this lift operator from lower levels, they span the old form space, and then its orthogonal complement is the new form space. Atkin and Lehner, we get a basis of this, of Hecke eigenforms. That's really what we're after. And then an additional one, I'm going to do a slightly more fine-grained decomposition than you may be familiar with, is that we can further decompose these spaces of new forms into twists from twist minimal spaces. So just like if you're working level 25 and you want to know the cusp forms, you don't want to know all the forms from level 5 again. So we rule out the old forms. Similarly, if you're working level 25, there may be new forms which are twists from level 5 or from level 1, and the orthogonal complement of those, the ones that aren't twists from lower levels, we call the twist minimal space and the twist minimal forms. They're new forms, eigenforms, which aren't twists from lower levels. That's all that is. Alternatively, there's this construction of cats, which I'm not going to go into detail in, because probably everyone in this room knows more about than I do, given the cohomology aspect of it. And this is an alternative definition over any Z1 over N module via cohomology. And if you don't know this sort of construction, there's an excellent exposition by Weiser, which goes into full details on every step of constructing it this way. But important for us isn't really, we're not going to really go into detail on the definition. What's important for us is really two results. They were there in the original paper. Firstly is if we take characteristic 0, we just get everything we wanted, everything we're familiar with, just the classical forms. And then secondly is that if weight isn't 1, we can project coefficient-wise, exactly as you'd expect the basis elements, onto our closure of the finite field, and that's going to be surjective. So, as you'd expect, you've got these forms, you project them into a finite field, you get these cats forms, and that's the whole story. As long as we're working k greater than 1, that's the entire picture. As I mentioned earlier, there's a problem with k equals 1, is that we've got these ethereal forms, so this isn't quite to help us all the way, but it will help us when k is greater than 1. The other side of that bijection had these Artin representations. So this is a continuous, it's a Galois representation of the absolute Galois group of Q. And continuity here just means that rho is going to factor through some finite extension k over q. And in our bijection, it was two-dimensional, so this GLNC is really GL2C for everything we're going to be doing. The projective image must be a finite subgroup of PGL2C. So there's only certain things it can be. We could be looking at dihedral groups. We could be looking at cyclic groups. We could be looking at A4, A5, or S4, and that's it. Anything associated with a dihedral, by that bijection from right at the start, we say is a dihedral form, and they span this dihedral subspace. There's a reason why I'll explain later, there's a reason why we pick off the dihedral subspace specifically, and then their orthogonal complement we call exotic forms, and it's the exotic subspace. And as a little note, is that forms in this exotic subspace must be associated with Artin representations A4, A5, or S4. We can rule out cyclic because the bijection right at the start said it had to be irreducible. So we really get two kinds of subspaces in our further decomposition. We've got the dihedral subspace, and we've got the exotic. So before I talk about the space that we're really interested in computing, let's talk about some sort of slightly related ones that will help really. Firstly, also all of the names on this, Young didn't discover Eisenstein series in 2019. All of the names on this are just really good reference points to find out great expositions on what we sort of know today. So Eisenstein series, there's this wonderful paper by Young with Fourier expansions, with basis change formulae, all sorts. We know basically everything that you would want to know about these Eisenstein series computations. How about working weight at least 2? Well, we know the dimensions. We can get the Fourier coefficients quite quickly and easily. There's the modular symbols method, great explanation of that. I think that's how SAGE works. And there's the Eichler-Selberg trace formula, which is how Pre goes about things. And then how about if we work over a finite field? Well, you can compute weight 1 forms in that case. But remember that will include the ethereal forms that we don't want. But you can compute those. There's the Hecke stability method, which is the one I'm going to be focusing on. I think it's generally seen as the fastest method. But there is also sort of modular symbol analog going on there. And then this is really why I separated out dihedral from everything else, is that the dihedral subspace can be computed really quite quickly. So Buzzard's explanation of that is fantastic, and that's now been done by Drew Sutherland up to level 40,000, who very helpfully gave me this data in all sorts of different ways when I kept on changing my mind on how I wanted it. So thank you very much to him. So now, how have weight 1 cusp forms, how have weight 1 new forms really been computed previously? Well, there's this general approach which immediately arises from the previous slide. Firstly, we've got this nice fast computation over a finite field, but it might include stuff that we don't want. And then also we've got the fast computation of the dihedral subspace, but that's not the whole picture. But we can start by step 1 computing both these subspaces. And if the dimensions are equal, great. The weight 1 space is just the dihedral space, and that we've already got everything that we wanted. So that's fantastic. But what if it's not? Well, then we just have to actually do the computation that we said we were going to do, and this will be by some slower method. This general approach has been adopted a number of times. Yeah, Buzzard 2014 got up to level 1500. The LMFDB subsequently got up to level 4000. I think that's also been done more recently by Bill Allenbear, who got up to level 5000 before changing tack. And the general complexity of this is order n to the 4 if you want to go up to any level n. And so had we just asked to do this again all the way up to level 10,000, which we computed up to, we would have expected it to take around 16 days. But you will see shortly that our computation was quite a bit faster than that. So what is that method that I mentioned for the slower method to actually compute the weight 1 space? Well, it starts by noticing that if you have a weight 1 cusp form and you multiply it by an Eisenstein series weight 1, very easy to compute with a conjugate character, then you end up in a weight 2 space with trivial character. And the Hecke stability just reverses it, finds a way to reverse this. So it says if you've got some Eisenstein series and you've got a form and you multiply up into this weight 2 trivial character space, but also the original function you started with was Hecke stable, then it must be a weight 1 modular form. And this works for any of the Katz constructions. So this works over any z 1 over n module. And this immediately suggests a way that we might compute weight 1 forms. All we do is we compute the weight 2 space, we compute an Eisenstein series, all it's very easy to do. We divide the space by the Eisenstein series, we find a TP stable subspace for some p not dividing n. Another result of Schaefer is that we don't actually need it to be stable under every Hecke operator. We can pick one specific Hecke operator, and as long as it's stable under that, we ended up with the subspace of weight 1 modular forms. Remove the Eisenstein series, remove the old forms, we've got what we wanted. We've got the new forms. So if f here is q bar, then we can just pick any p not dividing n. For f not q bar, so we're working over a finite field, we need a special value of p. And this is a bit of a problem, really, is that if you apply Schaefer's method directly to finite fields, that special value of p for high level ends up being absolutely gigantic. So it becomes slightly less feasible the higher up you go. But luckily we won't need that because we will be secretly working over q bar. So what's our method? Well, firstly, we've got a more efficient method of computing this weight 2 space from a previous paper on computation of weight 2 and above. So we can get our initial weight 2 space a lot quicker. And then also, we carefully choose our finite field so that the forms, the projections that we get onto that finite field, we can actually recover the original forms over Q from that. And then I mentioned that if we're working over FQ, we're going to end up with also ethereal forms. Also from the last slide, I mentioned that for a finite field, you kind of need to choose a special P, and I'm not choosing a special P. So we might end up with some modular functions as well. This lifting process will give us all the forms we want, but will also give us noise coming from the ethereal forms and coming from the modular functions. And so our final step is just to verify these forms. Why is this an improvement? Well, because we'll have hardly anything. We don't need to recompute everything over Q using using the Hecke stability method over Q, which was very slow. We can just verify the forms that we've got, and that's a lot quicker. So putting all this together, we were able to compute up to level 10,000, and it took a little under 14 hours. So this is a big improvement over previous methods. So now I'm going to talk a bit about, I'm going to talk about the weight 2 computation. But before I start that, I'm going to talk about twist minimal characters. So these have been important in both computations of all weights. And it allows us to significantly reduce the number of spaces that we actually need to compute. So the first thing to notice is that if I computed level 5, weight 99, and either of the order 4 characters, and then I did that computation, and then I said, OK, now I'm going to do the other order 4 character, you'd say, stop. You've already got everything, because it's just going to be the conjugate space. You don't need to do anything for that other character. But there's more to the story than that, is that if I said I was going to compute one character, and then I was going to compute another space with the character in the same Galois orbit, you'd again say that that's a very silly thing to do, because as long as we compute it in terms of some zeta, and just treat it as like a polynomial, then we can just embed it into every element in that Galois orbit. So job done. But there's one more step still, which essentially is the idea, the concept behind this twist minimality, is that if you compute then there could be other spaces where you twist into that space and it's the same level. So as long as we've computed one space, we get the other level for free, even though it might not be in the same Galois orbit. An example of this is that if you've got the trivial character space, you don't need anything which is a square character as a result. Even though it might not be, well, it won't be in the same Galois orbit, you get those for free because they fix the level by twisting. So this is the driver behind the definition. Again, the definition is fairly involved depending on what primes you're working with. But you can find definitions in the adelic context in Palm or in the classical context in Buckley and Strombergson or my previous paper. Yeah, it's just a minimal set of characters such that all new forms are twists of forms with twist minimal character. So we only need to really study these twist minimal characters in order to get everything. Why is that great? Here's an example for level 343, that's 7 cubed. And these red dots are the only representatives of twist minimal characters. So for this level, we have 200 odd characters, of which we have maybe, I think it's 12 Galois orbits, but we only need to compute 6 of them. because there's only 6 twist minimal. In particular, notice that level, so here I've categorized them by conductor. So we've got trivial character in the middle, and then this outer ring has conductor 343. And in particular, nothing conductor 49 is twist minimal. So we don't need to compute anything conductor 49 level 343 in order to get everything. So with the computation of weight 2 forms, we have these twist pairs. And the idea of these twist pairs is it's going to be, we want the trivial character space, and this is going to tell us lower level spaces that we need to compute with twist minimal character so that we can recover our trivial character weight 2 space of level n. I've put this up because I felt it was more relevant, but really the only thing to notice here is that when you've got an odd square factor of your level n, there is going to be more than one twist pair. So it's going to be a meaningful decomposition whenever our n isn't square free. And what we find is we give a formula for the polynomial coefficients of a, in all of the conditions, the lowercase psi is sort of any element in the orbit of, because all of the conditions refer to any element in the orbit of our capital psi. So what we get is, so this is equivalent to that Galois orbit thing, of this trace form, and we're going to have some homomorphism which sends it into whatever field we're working over, so it could be an embedding into C or whatever, such that any of those homomorphisms give us a element in the twist minimal space with character psi squared, twisted back by the conjugate of psi, so it gives us element in this weight 2 level n trivial character space. And the very start of the paper, what we do is we state exactly which twist pairs do we need, which homomorphisms do we need, which Hecke operators do we need, which lift operators do we need in order to get the basis that we want. And we can do this all over a finite field because of that result that I said of Katz, which is that as long as your weight is greater than 1, it's surjective. So we get a weight 2 trivial character basis by doing this. Why is this, what exactly makes this so much better? Well, the computation up to the nth Fourier coefficient, d basis elements, using any trace formula, so this could be the just the cusp-form trace formula, it could be the new form trace formula that the LMFDB was using, or it could be this twist minimal trace formula. It's got complexity. The number of coefficients that you want multiplied by the dimension all to the 3/2. And here's an example, level 175. So this picture gets even better the higher level you go, but I picked a low one as a nice example. Is that the full cusp form space is going to be dimension 15. The 2 relevant new form spaces, 9 and 3. And then the twist minimal spaces which are relevant. So these are twist minimal spaces with twist minimal character. Notice that we only have to even compute 2 different characters. Is going to be a much better computation. So what exactly do we do? Well, in Young's paper, he talks about these essentially a new form, old form analog for Eisenstein series. We can take new form Eisenstein series over our finite field, and we're going to pick Q to be congruent to 1 mod the Euler totient function of n, but later we're going to pick Q to be slightly more carefully selected than that. But for now, it just needs to be this. Then what we do is we find the intersection of that space divided by each of the new form Eisenstein series, the intersection of those, and we take the TP stable subspace, again, P is just the least prime not dividing n, and what we get is some noise coming from ethereal forms or from modular functions, but in addition to those, we have anything that's a projection of a modular form, we have the cusp form space that we were after. So what do we do next? Well, we turn this basis that we've got that sort of purports to be the weight 1 cusp form space. We have all the old forms because we've already computed every lower level, and we construct a basis which is the same rank, and we just put all of the old forms on the left. And when we do that, any Hecke operator is going to act like this. There'll be some square matrix in the top left on how it acts on old forms. We're going to have zeros in the bottom left. And we're going to have another square matrix in the bottom right, which I called a new, but of course not everything there is going to be a new form. By finding the eigenvalues of any TP, we will be able to construct eigenforms of our new form basis, of our purported new form basis. So how would we do this? Well, we need it to be we need all of the eigenvalues to be distinct in A new, and we also need them to be distinct from A old, eigenvalues in A old. But there's a good hope, because we've computed up to the Stern bound, there's a good hope that we can find some linear combination of Hecke operators that can do this. Indeed, in practice, there was never a problem. Of interest might be that what happened, how do we exactly find these, because we're working over a finite field? Well, we find the characteristic polynomial, and we factor it. But what if we don't, where we have a factor that was not a linear factor? That won't actually matter, because if we found something that's not a linear factor, that means that the Hecke eigenvalue isn't in this field, this FQ. But a weight 1 form would have to have all Hecke eigenvalues in our field FQ. So if we found something which isn't a linear factor of the characteristic polynomial, we can just throw it away. We know that it must be coming from either ethereal forms or modular functions where there isn't this restriction. So we only look at the linear factors, and that allows us to produce sort of purported eigenforms for over FQ. So in terms of this, so we've got these purported over FQ, and we want to recover the forms over Q bar. How we're going to do that is we're going to look more carefully at this association via L functions. So the L functions coming from the Hecke eigenforms look like this, and the L functions coming from the Artin representations look like that. So this P is some prime ideal lying. So the P is some prime ideal lying above P. The Frob is any Frobenius element. IP is the inertia subgroup, and V is the fixed subspace under IP. So this fixed V could be 2-dimensional, 1-dimensional, or 0-dimensional, corresponding to so we're going to see that corresponds to the Fourier coefficients. So we can define Satake parameters on both sides of this equation. On the Artin representation side, it's going to be the eigenvalues of the representation restricted to VIP. On the new form side, it's going to either be the roots of this polynomial, or in the case where P divides N and the coefficient is 0, then there's no Satake parameters and the space is 0-dimensional. Then the Satake parameter is just AP. And essentially the bijection that we had associates these two. Immediately, this gives us some useful things. So we have that Satake parameters must be roots of unity, and that gives us the Ramanujan-Peterson for weight 1. That there are some spaces where there's never going to be any cusp forms ahead of time, so we don't have to bother with these spaces as a result as well, because as in Asai or other papers, we would expect Fourier coefficients in this case for the Fourier coefficient AP, we would expect it to have size maybe, but it's a root of unity, so those things can't both be true, so there can't be any meaningful weight 1 cusp forms in that case. So an important step towards lifting is noticing that our Satake parameters, it can't just be any root of unity. There's a very place on the order of the Satake parameter. So this is a very key result which allows our lifting process. So if we have D being the lowest common multiple of all orders of projective images of Artin representations in the dihedral space, remember we know all of them, and so yeah, D is that, and then we have H being twice the LCM of 6D, or the total function of n, and D, then all of our Satake parameters are going to have order dividing this H. I don't have a full proof of this, but I will give a couple of the reasoning. So the action of, so we have this isomorphism, which you've probably seen, to be honest. If we have a matrix in GL2C with eigenvalues alpha and beta, then the associated matrix by this isomorphism in SO3 has eigenvalues alpha over beta, beta over alpha, and 1. But we know that it's dihedral, or we know that it's A4, or we know that it's A5, or we know that it's S4. And we very well understand the representation theory of finite groups. So suppose we've got projective image Dn. This gives us a 3-dimensional representation of Dn, but we know what the character values of that can be. Certain things. Let's say it's got character value. Let's say it's got character value 3. Then you're adding up 3 roots of unity to get 3. What can alpha over beta be? What can beta over alpha be? There's only a certain number of things. So we have the order of alpha over beta restricts to the LCM of 4 and n. And we can do similar reasoning to this with A4, A5, S4, and the end upshot is that everything must have order dividing this H. What does that mean? Well, it means that if we choose our finite field very carefully, so we choose field Q now to be congruent to 1 mod that H, that big H. Then we fix this ring homomorphism going from Z1 over M with Z to H into our field. Notice I've dropped the bar because we no longer need it to be the closure. We've got everything that we need is just in FQ. We fix the ring homomorphism such that the restriction to this Z to H is injective. You can probably see where this is going. In a second, we're going to have our forms over FQ, and we can work out the Satake parameters over FQ, and then because this is injective, we can work out what they would have been over Q before the projection. So we take the pre-image of the Satake parameters under our homomorphism, and this gives us Satake parameters over Q. From those Satake parameters over Q, we work out AP for all of the P, and then by the Hecke relations, we have our form that we wanted over weight 1 over Q of weight 1 new form. I've got a question mark there because it might not be. It might still be the noise coming from modular functions. It might still be the noise coming from ethereal forms. Just a side note, in practice, it never was. In practice, this question mark didn't need to be there all the way up to level 10,000. We had a problem, and the verification step, which is annoying, wasn't actually necessary ever. But we couldn't prove that it was always going to be unnecessary. So there exists a subset. It's not necessarily exactly the same, but there exists a subset of the functions produced by this method, which are the eigenbasis that we were after. Why is this so much better than before? Well, because before, when we got to this step, what we had to do was say, our dimension is slightly bigger than the dihedral space. We're going to have to start afresh over Q. In our case, if our dimension equals the dihedral space, job done. If it's slightly bigger than dihedral space, all we have to do is verify the forms that we've got. We don't have to recompute anything. So what's the verification look like? Well, it's sort of the Hecke stability method again, but the other way around this time. All of our functions now are Hecke stable. We've forced them to be. We've constructed them via the Hecke relations, so they have to be all Hecke stable. So all we do is we multiply them back by the Einstein series over Q and check if we end up in the weight 2 space that we started with. Yeah. So this is a quick example, and this is probably the worst example to prove my point. But these are the first exotic forms, level 124. What we do is we end up with 2 forms that are purported, and we just have to multiply both those forms back by an Eisenstein series and check if it's in S2, as opposed to starting again with the 14 elements of the weight 2 space and dividing them by this Eisenstein series all over again over Q. So we can see it's much better in our method here. But the reason this is quite a poor example is that this is probably as you get higher and higher level, you are going to get far more than 14 elements that you're going to need to divide, whereas frequently you only have 2 exotic elements or something. So any higher level is a better example than this, but this is a simple one, I suppose. One last thing that I'm going to mention is which spaces do we even need to compute? So we have all of the dihedral subspaces, but many spaces can't possibly produce exotic forms for various reasons. A character, firstly, we only need twist minimal characters because everything else we can twist to. We say a character has exotic potential if the character is odd. Of course, we don't need to check even characters for weight 1. If for any prime where a p maximally divides the level n, the character is not trivial. So if the character was trivial, then that corollary from way back it gets in the way and says no weight 1 forms here. So we need, in this case, the character not to be trivial. Also, whenever the character chi-p is primitive, then we want the order to be in 2, 3, 4, or 5. This is to do with those groups, the A4, A5, S4, can only have elements with these orders. And for any 2 such primes, we want it not to be 20. That's because the 5 only appears in A5, and the 4 only appears in S4. So you can't have them. You can't have them both. And so then the final number for our computation is we want to compute up to some level n max. We only need to compute a specific level if there could possibly be an exotic subspace there, or if we later want to compute a level which has an exotic which could have an exotic subspace, and we're going to need the level that we're looking at as old forms when we do that old form removal and diagonalization step. So we say if we look at for the least multiple of n such that m and chi have exotic potential, if it's greater than the level that we actually wanted to compute up to, then, or if there's no such level, then we don't need to bother computing it. And otherwise, computing everything else gives us the dimensions and Fourier coefficients of all the exotic forms with level at most m max. Thank you for listening.